A fundamental security feature of modern operating systems is some form of isolation enforced upon running applications, and on iOS this is known as the App Sandbox. The sandbox is what stops random apps that you install from being able to read all of your messages or access each other's files, but it also helps to reduce attack surface to the wider system as much as possible by providing access only to system functionality that is absolutely required by a given process, and this makes exploitation more difficult for attackers. The iOS kernel contains a huge amount of code in its core and also in various kernel extensions to help with things such as hardware accelerated graphics, media decoding, and more. It would be wildly irresponsible to allow every application to call into these kernel subsystems as they please, because doing so would expose deep, complex code to attackers, and the chance of them being able to reach a vulnerability would be high. To deal with this, the sandbox implements a filter that restricts what processes are actually allowed to do, by either allowing or denying a requested operation depending on which process is trying to perform it. This filtering logic is implemented at the kernel level in the form of small hooks. These hooks are added to kernel function handlers for pretty much every operation that a process in Userland might want to perform, including everything from file access to system calls and IOKit driver interfaces. For example, when a process wants to open a file at a specified path, the open handler function in the kernel will first call out to a sandbox hook function to evaluate if this requested file path is allowed to be accessed by this process. The same is implemented for executing system calls or opening connections to IOKit kernel drivers. The logic that actually performs this evaluation traverses that process's sandbox profile to find the requested action, evaluate any entitlement requirements, and eventually reach a determination of either allow or deny. A sandbox profile is a preset list of rules defined for a given process. Traditionally on macOS, these profiles are stored in plain text in .sb files, and they are easily readable. They use a Lisp-style syntax to define actions, parameters, and basic logic. On iOS, these profiles are actually compiled down to a proprietary binary format and stored directly in the iOS kernel cache binary under the symbol name collection data. This binary data is obviously not human readable, and so it must be first decompiled by custom tooling if you actually want to investigate which actions are allowed for a given process. The popular tool Sandblaster has been capable of decompiling iOS sandbox profiles since around iOS 7, and the tool has been consistently maintained by a few different parties over the years, with Celebrite's latest fork being updated to support iOS 26. Running the tool for version 26.2, you can see a bunch of .sb files in our output directory. These files are each named after the process that they are associated with, and they contain that plain text Lisp-style language representation of the profile that we can actually read. As you can see, each process on the system is given its own sandbox profile tailored to its specific needs. There are many Userland helper processes on iOS that act as a proxy for kernel interfaces. For example, ANED is a proxy process for making Apple Neural Engine requests. It implements the logic to communicate with the Neural Engine interface in the kernel, which includes the loading of machine learning models, executing them, and passing data to and from the Neural Engine itself. A regular application like Instagram does not need direct access to this kernel driver. Normal applications are assigned a very generic and restrictive sandbox profile, giving them access only to some essential drivers, some Userland processes, and some specific file path access. Using a proxy process to talk to risky kernel code is a much smarter decision from a security standpoint. If an app like Instagram does want to run some kind of machine learning code and it requires the use of the neural engine, then it can make a request to the ANED system process via an IPC message. It will ask the ANED process to perform a specific task, and ANED will in turn make the appropriate request directly to the kernel driver. Any results that need to be sent back can be delivered to the calling process also via an IPC message. So how are these sandbox profiles actually attached to specific processes? Let's explore the sandbox on a real jailbroken phone so we can see how it works live in kernel memory. By the way, if you appreciate the research effort that goes into making these technical videos, leave a like on this video and subscribe to help support this channel. Here I have a normal iOS app that is trying to open a connection to a privileged kernel driver interface, the IO Accessory Manager driver, used for dealing with connected accessory devices. This app is installed as a regular application, and so upon launch, the kernel assigns it the default container sandbox profile. This is the restrictive sandbox profile for all App Store and third-party apps. And you can think of it as similar to the untrusted app SE Linux policy used on Linux and Android systems. Trying to open a connection to IO Accessory Manager from within inside this app fails, and in the system log we can see the sandbox deny message stating that the IOKit open operation is not permitted for this kernel driver. One of the only processes that is actually granted permission to talk to this specific kernel interface is the user space daemon accessory_d. The sandbox profile for accessory_d allows this action. So what if we could just borrow that profile to use it for our normal app? It turns out this is a nice experiment you can actually try on an older iPhone if you already have kernel read and write capabilities on a jailbroken device. And it will provide some nice insight into how the sandbox profile is actually handled at the low level. Firstly, all running processes on iOS are represented by a proc structure in the kernel. The kernel stores all of these proc structures in a doubly linked list, and you can traverse this to find a given proc structure by starting at the kernel's own proc and then following the next pointer, checking the process ID of each subsequent proc along the way. We can do this and find the proc structure for our app that's running on the device. Each proc structure has a field known as the ucred, which holds a pointer to the credentials for this process. Inside the ucred structure is a pointer to that process's MACF label, which eventually leads to the entitlements for this process and a structure holding the sandbox data. The first member in the sandbox data structure is a pointer to the static sandbox collection binary blob, the one that is stored directly in the kernel cache. And then just below that, we see a much smaller value. This is the offset value, which is relative to the start of the sandbox collection to get to the specific sandbox profile within the collection that this process has been assigned. So on our jailbroken device, we can actually just borrow or steal the sandbox profile offset from another process, such as the accessory_d process, and write it into our own process's sandbox structure. Or better yet, if you want the entitlements of the other process too, then you can actually just replace the entire ucred, which encapsulates both. This effectively copies all of the in-memory entitlements and the sandbox profile of that process and applies it to our own process at runtime, which ultimately has the effect of upgrading our credentials to that of accessory_d. So without doing anything else, with our app still open and running on the device, now when we try to open the connection to IO Accessory Manager, the sandbox filter allows our requested action, and we successfully get a connection port to the privileged IOKit user client from that driver. This serves as a nice demonstration of how the sandbox works, but it can actually also be very useful for research purposes if you're digging into one of these more privileged kernel drivers and you need that access. This technique of stealing process credentials was actually used in many jailbreaks to elevate privileges on the system post-exploitation. Apple of course wanted to put a stop to this, and so in the modern day we see additional protections preventing this type of post-exploitation technique. Processes these days now actually have a second read-only proc structure, which holds all of the read-only data associated with a process. Within this read-only structure is the ucred, and the ucred structure itself is also allocated in a read-only memory zone, so that it cannot be tampered with once the process has spawned. These read-only protections are in effect from A12 devices onward, initially implemented on top of the page protection layer feature, but more recently enforced by the secure page table monitor. Therefore, on modern-day iOS, replacing a process's sandbox profile is not nearly as straightforward as it once was. So we've seen how the sandbox is implemented at the kernel level, and we've seen how, given kernel read and write on an older device, we can unsandbox our app by stealing credentials. But this is all assuming that we already have a compromised device. So what about in a real exploit chain? How do attackers actually break out of the sandbox? Hackers will typically require a sandbox escape as part of their exploit chain, because it is normally the case that interesting kernel attack surface is simply not reachable directly from their starting context. In order to compromise the entire system, they might first attack a Userland system process with the aim of leveraging its sandbox, which may provide them additional attack surface to the kernel. Let's assume that an attacker is starting their exploit chain from within the browser context, and they have successfully exploited a WebKit bug to gain remote code execution within the browser process. Check out my other video on iOS browser exploitation to see exactly how this would work. They are now running their own code from inside the browser process and can access whatever the browser can access. Unfortunately for them, the browser process runs in a very restrictive sandbox profile with very limited access to kernel attack surface. Apple does this specifically because they know the browser is the most common entry point for an exploit chain, so they want to mitigate this by locking down that process as much as possible. As a result, if the attacker wants to next exploit the kernel, they probably need access to a kernel driver of some kind, and since they can't do this directly, they need to first exploit a different system process that can provide this access. Sandbox profiles define exactly which system processes a process is allowed to communicate with over MACF. You can see these listed under the MACF lookup operation in a given sandbox profile. So let's imagine that in our theoretical scenario, the browser process is allowed to communicate with system process A. System process A happens to be involved in the machine learning processing on the device, and so its sandbox profile gives it direct access to a privileged iOS kernel driver, the Apple Neural Engine driver. It's allowed to talk directly to this driver by issuing commands and running machine learning models. Now, if the attacker has also identified a vulnerability, a heap buffer overflow for example, within system process A that can be triggered through muck IPC communication, they can exploit this from their initial browser context. This may involve using their initial arbitrary code execution ability from their stage 1 exploit to send a malicious muck message to process A, triggering the heap overflow and gaining code execution there. At this point, they would have effectively hopped into this other process, escaping their initial sandbox and now having access to whatever this new sandbox context provides. Here, they might be able to trigger a kernel bug within the driver that system process provides access to, allowing them to compromise the entire system. This is known as chaining exploits. With each link in the chain, the attacker is essentially hopping into the next stage's context, gradually expanding their access to the system. Some exploit chains might even require more than one sandbox escape. It all comes down to the requirements of the reachable components and where the bugs are. We won't look at any specific sandbox escape exploits in this video, but let me know if that is something you'd be interested on seeing in a dedicated video down below in the comments. So in summary, this fine-grained control over what processes are allowed to do allows macOS and iOS to separate out functionality into designated processes and ultimately reduce reachable attack surface across the system. And in many cases where exploitation is still achieved, it provides a very nice level of damage control, limiting what an attacker can actually do, and normally forcing the use of additional exploits like sandbox escapes. Hopefully you learned something new in this video. Thanks for watching, and I will see you in the next one.